Let us now consider the rate of change of a vector, let's call it G, fixed to a rotating body. Okay? By fixed to, I mean fixed relative to a rotating body. Okay? Okay, so let's say we have some frame. Okay? And we have some other frame. And the second frame is fixed to some weird rigid body. Okay? And this frame, let's say, is fixed in space, and this frame is moving relative to this frame and is fixed relative to this rigid body. And we are considering a vector G that is fixed in this frame, but possibly moving in this frame. Frame B, oops, so that's a rigid body. Frame B is body fixed and rotates, well, with, let's just say, has angular velocity omega relative to frame O. Okay, frame 0. Okay, so this frame on this body is has a relative angular velocity omega relative to this frame. Okay, now let's say we have some vector G that is fixed in this frame. In other words, as this frame is moving, as this rigid body is moving, G in this frame is a fixed vector, but in this frame, because it's moving with this rigid body, is this rigid body in this frame, G is well, that G has a derivative in this frame. Okay, so let's see what that derivative is. Let's derive an expression for that derivative. Let's write the premise down. G some vector fixed or constant in the body fixed frame okay. Now let's draw a picture. Well, what's a goal? What is dg by dt in frame 0? Okay. Now, let's draw a picture. Let's say this is the axis, recall Chasles' theorem or Charles theorem again, and that theorem suggests that there's an instantaneous axis of rotation for a rigid body with some angular velocity omega. Let's consider this to be the axis of rotation, and let's call this some point C in that frame, and let's draw a little ellipse there. And let's say that we have the vector G like so. Okay. Wherever G is, you can transport it to this axis. Okay, so that's the vector G, and let's call this point P. And let's say in a small amount of time, delta t, so let me in a small amount of time, delta t, let's say it goes to this point. Okay, so let me erase this and write P here, and this point is P dash or something, and because it's rotating about this axis, we have right, that's the axis of rotation. We have let's say to G dash in frame 0 about axis n by angle theta, delta theta, in time delta t. Okay, so consider small period delta t, and what happens is we've rotated this vector. This angle is delta theta. Okay, so this vector has gone to this vector. This vector has gone to this vector by having rotated by delta theta about this axis. Okay, so this is the angle of rotation for that picture. Okay, so the vector delta G is, of course, G dash, the new vector, the rotated vector, minus G. Okay, so this vector minus this vector, and they can think write that as Cp dash minus Cp, or it's basically equal to Pp dash. Okay. Now what is that equal to? Let's call this point Q. The first property is that the direction of delta G, this vector, is, well, it's perpendicular to Well, by definition, it's perpendicular to QP because it's rotating about this axis and sort of rotating in a circle. And it's also rotating, it's perpendicular to N. Okay. So you can sort of think of it as like a view from this direction. You can just think of it so if you call this point Q, this point P, this point P dash, this small vector, this vector, clearly this vector for small deviations from P to P dash is perpendicular to QP as well as perpendicular to N, which is the perpendicular to this plane. Okay, so that's what's being written here. It's perpendicular to this vector and perpendicular to this vector, which is this is the top view. Okay, this view is looking down on N. Okay, so we know something about the direction of delta G. What is the magnitude of delta G? Okay, so magnitude of delta G, we'll show this in a minute, but let me just write down what it is. Magnitude of delta G, the vector, equals, it's, well, if you sort of look at this picture, it's quite clear. It's QP times delta theta. Okay, so if this is delta theta, it's basically this angle times this radius. So it's QP times this angle, which is, so let me just write that down. So this is the absolute value of the magnitude of QP and the magnitude of delta theta. Okay, that's what the magnitude of G is. Okay, so now we know the direction, we know the magnitude. Can we write an expression for delta G? So I'm actually just going to write an expression for delta G and then show that that expression satisfies these two properties and we are done. Okay, so the expression is delta G equals delta theta N crossed with the QP vector, okay, where this is the cross product. Okay, now if you take this quantity, because QP and N are perpendicular to each other, and N is a unit vector, the magnitude of this thing is just the magnitude of this thing times the magnitude of this thing, which is exactly this quantity. Okay, so it checks out in terms of magnitude. And in terms of direction, well, this is along N, this is along QP. The cross product of two vectors is perpendicular to both of them. And in fact, that's the direction of delta G. Okay, so this expression for delta G that we just wrote down agrees with these two principles or properties that we derive for delta G based on this picture. So this is it. That's delta G. That's gives you the change in G for a small amount of time. And then you can divide through by delta T. So we get delta theta by delta T N crossed with QP. QP, of course, is G. So delta theta by delta T N crossed with G. And then we take limits on both sides. Limit delta G by delta T, which is dG by dt, equals, well, we take the limit here. of delta theta by delta t n crossed with g. And of course, this gives us omega. That's the definition of omega, the angular velocity. Okay, so that's the definition of omega. Okay, so that's the key result. Let me just write it down again. So some vector dg by dt, the rate of change of that equals omega crossed with g. Okay, so this is one of the most important sort of relationships in rigid body kinematics. So what is g? G is some vector fixed in the rigid body frame, and this rigid body frame fixed to the rigid body is moving relative to some other frame with angular velocity omega. And the question is, if g is fixed in this frame, what is the rate of change of g in this frame due to the fact that this g is rotating with this frame? And this is just a quick derivation that the rate of change of g in frame 0 equals omega cross g, where g is the current vector in the body, is fixed in the body fixed frame.